Fluid properties are usually treated as continuous functions of position in a flow field, since their variations are quite uniform. For example, we don't usually think of flowing honey as being composed of individual molecules. This differs from the approach of basic kinematics, where the trajectories of individual particles or systems are studied. To analyze fluid mechanics problems, we most often use an Eulerian frame of reference, where we observe a fixed flow field rather than following individual moving fluid elements. In this Eulerian method, we study the properties of the flow pattern in terms of spatial position and time. In a few cases, it's more useful to follow a specific fluid mass through a flow field using a Lagrangian reference frame attached to the mass. Here, the blob of white water is followed as it moves downstream. But if we mark the instantaneous boundary of the blob of fixed mass at a certain time, then we can watch the water flow through this boundary while the original white blob flows on. This is the Eulerian approach. The Lagrangian approach works best, for example, in meteorology, where a weather balloon drifts along with the prevailing wind. This reference frame is inferior to the Eulerian approach, however, in treating the airflow through a jet engine. In this case, a control volume is fixed to the jet engine with air flowing through it. Likewise, an appropriate Eulerian control volume for this hairdryer is fixed to the dryer itself rather than to the air passing through it. In this simple example, the control volume has one inlet and one outlet, and its lateral sides are impermeable to the air. Electrical energy enters the control volume, however, in order to heat the air and drive the blower that moves it. The fundamental conservation laws, such as Newton's second law of motion, were originally written for a system of fixed mass, in other words, using a Lagrangian approach. In order to apply the more useful Eulerian framework in fluid mechanics, we need a mathematical way to translate between the two frames of reference. This is Reynolds' transport theorem, which makes use of the so-called material derivative. The rate of change of a property in a fixed mass system is given as the time rate of change of that property inside the control volume plus an advective term describing the net flux of that property through the control surfaces. Here's a high-speed visualization of gas emerging from an aerosol can. We could try to follow the gas as a system of fixed mass, but the phenomenon is easier to analyze if we draw our control volume around the can and treat the gas as an advective flux through the control surface. In all of these flows, it's important to appreciate the visual flow patterns as well as the mathematical analysis. There are four basic types of flow lines that we need to understand in order to interpret these patterns: streamlines, streak lines, path lines, and time lines. The streamlines are instantaneous lines of the flow, while the streak line, path line, and time line are generated over the passage of time. A streamline is a line everywhere tangent to the velocity vector at a given instant. The streamline comes directly from the mathematics of the flow, while the other three types of lines are often generated experimentally. Here are the streamlines for a flat plate fixed at a certain angle in a smoke tunnel flow field. These were measured by particle image velocimetry, or PIV, a modern tool of experimental fluid dynamics. A streak line is the locus of particles which have earlier passed through a prescribed point. It can be produced experimentally by the continuous injection of tracer particles at a given point in the flow. A path line is the actual Lagrangian path traversed by a given fluid particle. It can be observed in a time exposure of a single marked particle moving through the flow. In steady flows, streamlines, path lines, and streak lines are identical. A timeline is rather different. It is a line of fluid particles across the flow at a given instant, and it reveals the velocity profile. In unsteady flows, streamlines, streak lines, and path lines can be quite different. Here, the unsteady flow over a rotating plate is shown. When the flow is observed at an instant when the plate angle is the same as in the previous steady flow, we can see that all three lines differ. The streak lines and path lines, which developed over a time history while the plate was rotating, differ from the instantaneous streamlines. To understand fluid flows, we must first see them. Flow visualization is the science and art of observing fluid flows that are normally invisible. It should come first in any fluid dynamic investigation, since it provides us with an overall physical picture of the flow phenomena. Detailed measurements of quantities like pressure, temperature, and velocity are not likely to be understandable without such an overall picture in mind. Some flows are visible to the human eye without any assistance. For example, here we can see the evaporative phenomenon called wine tears merely by looking at a glass of wine with appropriate illumination. Differences in surface tension cause the wine to stream down the sides of the glass. Another example requiring only simple illumination to visualize the flow is the hydraulic jump caused by the stream of water in a kitchen sink. The hydraulic jump represents an abrupt change from so-called supercritical to subcritical flow. Here we observe the mixing of red and white paint stirred by a paddle. The flow is self-visualizing because the paint pigments reflect different colors of the incident white light. Eventually, given enough stirring, the two pigments become well mixed on a molecular scale, and we observe an intermediate pink hue. Similar mixing can be visualized in a computational fluid dynamics, or CFD, simulation by marking a blob of fluid particles red and following the distortion of the blob. For visibility, the red pigment is shown mixing with a transparent fluid. Here's a much more complicated self-visualizing flow. A white-hot jet of plasma melts its way through a steel plate. Surface tension effects determine how the molten metal accumulates on the bottom of the plate shown here. This flow appears to be undergoing some sort of periodic process. One of the simplest of flow visualization techniques involves the motion of an oil film on a surface. Here's a compressed air nozzle aimed perpendicular to a flat white surface. This flow is invisible without the assistance of a flow visualization technique. By placing droplets of colored oil on the surface, we can observe streaking caused by the shear stress of the impinging air jet. This is a simple example of the oil flow technique, a method of surface flow visualization. It gets a little more complicated when the jet impingement is not symmetric. Here the jet comes in at a 45-degree angle from the left. This technique is very useful in wind tunnel testing of aircraft models. It only indicates the flow direction very near the surface, but it's quite easy to use. Of all the different flow visualization techniques, we most often add particles to a flow to make it visible. The particles scatter light, as in this plume of smoke from a cigarette. Without the smoke particles, the plume would be invisible. In another example, particles of talcum powder were spread on a surface, and a dog was encouraged to sniff a treat lying there. From this, we see that the air exhaled by the dog's nose disturbs the talcum particles, and the subsequent airflow pattern is revealed. Here, the air surrounding a person is seeded with theatrical fog. When the person takes a walk, the fog indicates the airflow in his wake. A vertical sheet of laser light is used to illuminate a plane in the center of this complicated turbulent flow, known as the human aerodynamic wake. Next, a paint spray gun is aimed perpendicular to a sheet of plywood that appears edge-on in the video. Once again, laser sheet illumination reveals the paint particles. In this unsteady flow, the spray strikes the plywood, but not all of the paint is deposited. Some of the smaller particles escape in what is known as a starting wall jet. These overspray particles are a problem. They must be captured, or else they will cause air pollution. Another major category of flow visualization is optical methods. Typically, a beam of light is passed through the flow, and parts of the beam are refracted due to flow disturbances. The disturbance in this case is the heat shed by the human body, which creates a warm, turbulent plume, the human thermal plume. The subject is standing in front of a precise parabolic telescope mirror 1 meter in diameter, big enough to be the centerpiece of an astronomical observatory. Instead, it's actually the centerpiece of a Schlieren optical system, a laboratory technique for visualizing density differences in transparent media. Considering the human body as a heat engine, most of the calories we consume are rejected as waste heat, which is shed by thermal convection and radiation. Without the human thermal plume, our bodies would overheat with dire consequences. In addition to the particle seeding technique shown earlier, the Schlieren technique can also reveal the airflow from a dog's nose. The inhaled air is at room temperature and is not visible, but the exhaled air has been warmed inside the nose. We can see that it forms jets from the dog's nostrils that are aimed downward rather than straight ahead. A special Schlieren system is used to visualize very large flow fields. Here we see thermal plumes rising from a person and a computer. This warm air is removed at the ceiling, while the air conditioner on the left emits cool air that falls to the floor in a scheme known as displacement ventilation. We can use the same approach to study ventilation in commercial kitchens, where the heat and fumes from a griddle are collected overhead by a ventilation hood. The Schlieren method is especially useful to visualize high-speed flows in wind tunnels. Here we see Mach 3 airflow starting and stopping over a wedge-shaped model in a supersonic wind tunnel. Finally, some flows happen too fast to be observed properly by the human eye. High-speed imaging is required to slow these flows down. This milk splash requires no special visualization technique other than slowing it down by a factor of 33 using a high-speed camera. This Schlieren video of a supersonic air jet from a nozzle is shot at the usual rate of 30 frames per second, but each frame is exposed for only 1 microsecond. This is a kind of pseudo-high-speed imaging that reveals the radiation of jet noise from the flow. The shedding of a Kármán vortex street from a cylinder is graphically visualized in a soap film tunnel. However, the vortices happen too fast for direct observation, so a high-speed camera slows the flow down by a factor of 15. This phenomenon of Kármán vortex street shedding can also be predicted numerically using CFD, as shown in this computer animation. The motion of vapor bubbles in nucleate boiling is likewise too fast to follow with the eye, so the high-speed camera allows us to observe it at a convenient speed. These flow visualization techniques and others allow us to study and understand the kinematics of fluid flows.